In the Maori language, Rotorua means large lake. And Lake Rotorua is the largest water body in New Zealand's Te Arawa Lakes region. This beautiful windswept lake is polymictic, with continuous wind-induced mixing that during the warmest months of the year is interrupted by periods of stratification. During these stratified periods, oxygen is rapidly depleted, and the bottom waters of the lake can become completely anoxic. As in many lakes around the world, oxygen levels in Lake Rotorua are now tracked in the water column by a string of automated sensors moored in the lake. These show large fluctuations over short periods of time, from well-mixed homogeneous conditions to rapid depletion at depth during the periods of warming and stratification. This depletion reduces the quality of deep water habitats for the trout in the lake and results in the release of nutrients from the sediments to the water column. Dissolved oxygen is essential to the respiratory metabolism of most aquatic organisms, to the ecosystem functioning of fresh waters, and to the ecological quality of lakes and rivers. Oxygen is therefore considered the most fundamental parameter of lake and river ecosystems, aside from water itself. The distinguished American limnologist G. Evelyn Hutchinson noted that a skillful limnologist can probably learn more about the nature of a lake from a series of oxygen determinations than from any other kind of chemical data. These words underscore oxygen's immense value for insights into the ecological functioning of aquatic systems and for the sustainability of water for human use. In the past, oxygen measurements were traditionally made by taking water samples at discrete depths, followed by chemical Winkler analysis by titration in the laboratory. Today, in addition to continuous recordings with automated sensors moored in the lake or reservoir or river, oxygen measurements are usually made with a multi-parameter profiler that is lowered down through the water column. The instrument is typically fitted with an optical sensor for dissolved oxygen and additional sensors for depth, temperature, conductivity, and chlorophyll A fluorescence. The solubility of oxygen in water decreases with increasing water temperature. It also decreases with increasing salt content and with increasing altitude. Dissolved oxygen may be reported in concentration units of milligrams or micromoles per liter, or as percent saturation, where 100% is the oxygen concentration in surface waters that are fully in equilibrium with the overlying atmosphere. There is a precarious equilibrium between processes that produce and consume oxygen, and therefore large deviations from 100% saturation are often observed in lakes and rivers, including sometimes a shift to complete loss of oxygen, that is, anoxic conditions, with associated changes in ecosystem services. This variability of oxygen dynamics in inland waters results from the combination of exchanges with the atmosphere, advection, dispersion, and biota-mediated transport, photosynthesis and photorespiration, aerobic respiration, oxidation of reduced inorganic compounds, photochemical oxidation of organic matter, and chemical weathering. Most of these processes are directly or indirectly mediated by organisms. Surface and subsurface water flows are of paramount importance to understanding oxygen dynamics in rivers. Lateral and vertical flow pathways are involved in the advection of dissolved oxygen, as well as in the transport of other substances indirectly influencing riverine dissolved oxygen dynamics, such as organic matter, nutrients, and electron acceptors. The oxygen content within small high-gradient streams is usually near saturation due to the high turbulent mixing of the water. However, marked variations occur spatially and temporally in low-gradient streams and rivers. dissolved oxygen can vary on diel, seasonal, annual, and decadal scales. And these dynamics depend on the hydrological and biogeochemical conditions of the river catchment. This spectrum of temporal signals combines to shape the oxygen dynamics of a river. Similar to rivers, oxygen concentrations in lakes vary on diel, seasonal, and annual timescales, and spatially on horizontal gradients between littoral to pelagic sites and vertical gradients with depth. On an annual scale, dimictic north temperate lakes exhibit 4 patterns of oxygen depth profiles. Orthograde, which is typical of ultra-oligotrophic lakes in summer. Clinograde, typical of many lakes, including eutrophic lakes in summer. Positive heterograde, caused by deep photosynthetic maxima or by interflows. And negative heterograde, caused by deep maxima of heterotrophic activity or inflows. The seasonal pattern of oxygen dynamics varies enormously among lakes, depending on their mixing regimes throughout the year. From permanently stratified lakes, such as perennially ice-capped Lake Bonny in Antarctica, where there is little variation, to large seasonal variations in lakes that mix once monomictic, twice dimictic, or many times polymictic each year. Lakes globally are exhibiting decreased oxygen concentrations in both their surface and bottom waters. And predicting and managing these shifts requires attention to both climate warming and to land use changes. Dr. Kaylin Carey is Professor of Freshwater Ecosystem Science in the Department of Biological Sciences at Virginia Tech in Blacksburg, Virginia, United States. Her research aims to understand the feedbacks between human activities and lake and reservoir ecosystems. And her laboratory applies a variety of methods, including field studies, data science, and modeling. Here she describes the importance of monitoring dissolved oxygen and approaches towards modeling the oxygen dynamics of inland waters.
I'm a professor at Virginia Tech, and I love studying dissolved oxygen because it is such an important indicator of the ecosystem functioning of lakes. According to Wetzel, dissolved oxygen was the single most important measurement that a limnologist can make. A lot of my work is focused on trying to predict and forecast oxygen in lakes. The duration of anoxia, or very low oxygen conditions, can be predicted using regression-based models with variables related to lake morphometry, hydrology, and trophic state as predictors. In reservoirs, variables such as hydrology and organic carbon and phosphorus loads sometimes work better. We can also use process-based models to predict oxygen deficits at smaller time steps, such as daily. As oxygen conditions are changing in many lakes, reservoirs, and rivers around the globe, it is vitally important that we continue to monitor and model these dynamics as they provide such an important control on water quality.
In reservoirs, the distribution of oxygen is highly variable, both horizontally and vertically. As illustrated here in Falling Creek Reservoir, a hypolimnetic anoxic zone often develops in summer and expands horizontally and vertically through the reservoir until fall mixing and circulation. Anoxia and hypoxia are among the most acute environmental problems facing inland waters. Their prevalence has rapidly increased and likely will become even more frequent in the future. Metrics to assess anoxic and hypoxic conditions are based on oxygen values, on calculation of the rates of oxygen consumption in the hypolimnion, and on the duration and extent of anoxia in lakes and running waters. An approach for lakes and reservoirs is to estimate the rate of oxygen depletion in the hypolimnion during the period of summer stratification. This can be calculated per unit volume as the volumetric hypolimnetic oxygen demand, or integrated throughout the hypolimnion and expressed per unit area as the areal hypolimnetic oxygen demand. An example of the volumetric approach is a study here at Lake Pupuke, an urban lake in Auckland, New Zealand. The lake occupies an extinct volcanic crater, and continuous monitoring showed that it loses its oxygen in the hyperlimnion each summer. To calculate the volumetric hyperlimnetic oxygen depletion, VHOD, for the lake, oxygen concentrations were averaged for the depth stratum 20 to 30 meters. These values were then plotted against time, and a regression line was fitted to the period of summer stratification. The slope of this fitted line gave a VHOD rate of 0.054 grams per cubic meter per day. This was 26% below the value measured in the 1960s, when the lake was responding to eutrophication by farm and sewage inputs. Anticipating the effects of climate change on the oxygen dynamics of inland waters is challenging, because shifts in climate will be accompanied by changes in many other factors influencing oxygen concentrations. The impacts of climate change on oxygen solubility, stratification, respiration rate, stream flow, nutrient sources, and extreme weather events will all combine to shape the future prevalence of oxygen deficits.